So today we're going to talk about software testing. Now, why do we need to test our software? Let's think about it for a second. Why do we test software? Well, we test it because we want to be able to fix those bugs and perhaps some badly implemented functionality in our code, which can lead to annoyed users and unhappy customers. Now, since we're talking about cybersecurity here, let's think about it from a cybersecurity perspective. We're going to test software because we attempt to catch those bugs that can potentially become future vulnerabilities, which can lead to exploits, which can lead to attacks, which can lead to data breaches, which can lead to, again, annoyed users and unhappy customers. So basically, we're going to talk about, let's see how we can keep our customers happy through software testing. And kind of the bad news here is that this process is incredibly difficult. There's probably no piece of software in this entire world that hasn't had at some point in time some issue, some bug, some badly implemented functionality which required a patch, a fix, an update. And that's just how things are. I mean, software assessment and code review are never going to be able to catch absolutely all problems or possible issues with that piece of code. So we're actually in a process where we're not attempting to eliminate all potential problems, but we're trying to minimize and bring down the number of potential problems as low as possible. And one more thing to keep in mind, we can only fix those things that we know about. We can only think about so many issues, so many potential vulnerabilities, but there's always going to be someone who comes after us and discovers a new flaw in our code. And unfortunately, there's not much you can do about this except continuously try to improve these processes, these software assessment processes. Now, this chapter, this discussion is going to be more about terminology. It's not going to make a software tester out of you, but at the end of it, you'll be able to understand it, explain it, you'll be able to talk about it, and of course, you'll be able to pass the questions on the exam, of course. All right, so enough talk. Let's bring some order to this process and let's see what are the main methods that we can use to improve and actually test our code. And well, the first one we'll address here is going to be static analysis. And whenever you see static analysis, just think about, looking at the code. So we're just going to look at the code and analyze the code for potential weaknesses that can lead to vulnerabilities. And remember, this is going to be performed before the code is ever run or even compiled. And when I say just look at the code and analyze the code, you're probably imagining a situation where you're just reviewing someone else's code and you see a function right there that, I don't know, that function doesn't look safe to me. And yeah, that's one way of doing it. That's a manual code review. But of course, we're going to try to automate this as much as possible because some automated tools might have some better insight and better intelligence and better attention to details, let's say, than our human peers. Now, just to give you a starting point here, NIST has a list NIST has a list of popular source code security analyzers. So these are going to be automated tools that focus on security first of all. Now, of course, this list is very comprehensive and you can see that most of these tools right here are focused on specific programming languages because if we were to check for specific conditions, well, we do need the tool to properly understand the code that we're writing. So they have to be designed specifically for our programming language. Some of them are free, some of them are, let's say less than free. And don't be put off by the fact that some of them haven't been updated in a couple of years. They're still more than okay since the core principles in most programming languages don't really change that often. Now, you might be able to recognize some of these. For example, let me see here. PyLint, if you ever programmed with Python. PyLint is a free tool here for checking for errors and looks for bad code smells. This is actually an official term. If you're not a programmer, this might be new to you, but code smell is a characteristic of code, of source code, that can potentially be a red flag or something that doesn't really look well and can lead to potential problems. When I see smelly code, I keep thinking about smelly cats from Phoebe in Friends, but let's not digress too much. And of course, you can do all this code checking business manually as well. And if it's done manually by human eyes, it's usually called peer review or manual peer reviewed, simply because you do need a peer. You do need another human being next to you to review your code. Now, that peer could be a programmer, but can also be a security analyst, just like you, who understands programming, of course. Unfortunately, most developers nowadays kind of skip this part and only focus on functionality, so security is kind of an afterthought or is considered to be somebody else's problem. And just as a piece of advice here, since we're talking about human interaction, when you're doing code review, try to, focus on the communication, try not to offend, don't just criticize, because you're finding flaws in somebody else's work. And this is something that's most of the time really tough not to take personally. And of course, if you're a team lead or working with some programmers, the recommended way to approach this step right here is to train your developers from the beginning on at least basic security concepts, or at least give them access to some simple tools that they can use during their initial unit tests. Now, what comes after static? Dynamic, of course, but we're going to have a bit of a longer discussion about dynamic analysis, and I'm going to leave that to the end of the video. In the meantime, let's focus on the formal method. Now, the formal method is going to be completely automated, and it's actually a type of software verification that relies on mathematical inputs which track code execution. So it basically allows you to check which code paths in your application are being used, which code paths are perhaps unreachable, which code paths could potentially create an infinite loop, an undesirable infinite loop. And it's mostly going to apply to more complex projects where the number of branches and potential code execution paths is just too high for a programmer to be able to follow all potential code execution scenarios. Now, while static testing required that the automated tool to understand the programming language that you used to write your code, well, the formal method requires the software tool to actually understand the application that you're developing and how is that application supposed to be used. So you're basically going to have a very well-defined formal model of the application for that tool to be able to understand what should be the possible code paths, what branches are supposed to be taken, which end states is the application supposed to end up in, and stuff like that. Now, having a complete formal model of an application is not going to be an easy task. It's something that it's not always possible. It's not easy to accomplish. So not every company and not every software development team is going to be able to implement this. Now, AWS does this, and since we're talking about Amazon, no surprise here, they can afford to do this. And this is one of their papers focused specifically on the security of all their cloud services. So, for example, you can see here that the AWS security team performs this formal security reviews of all their features and services, which were about 1,400 back in 2017. So yeah, that's going to be a whole lot of effort to develop such a model, but it's going to provide you with great benefits because it's completely automated, and it also has the best chance of figuring out all the possible execution scenarios of your code, or the possible scenarios in which your application could be used, which is awesome from a security perspective. You're basically not going to be taken by surprise by any of your application's behavior. Another one that you've probably heard before is UAT, also known as user acceptance testing. And as the name says, it's going to be focused on the users, and we're basically going to be using the users as software testers. Now, most of the time, this is going to apply in a scenario where you're developing an application for a company, for a customer, and specific individuals from the customer side volunteer or have been volunteered to test your application, which is still in a pre-release state. It is in a so-called beta version. Now, of course, this kind of testing is not going to be performed the same way your developers are going to test your code. Now, the users are going to be testing the interface of your application, and they're going to be following some predefined guidelines. So basically going to have some documents here that state the fact that the application is not in its final state, and this is precisely what we need to test right now. Now, they might follow those guidelines or they might not. So UAT is sometimes both a source of interesting feedback and testing results, but also a source of frustration from the customer because they realize that things that they expect to work don't work yet, or they don't work at all as expected. But this is more about politics than cybersecurity, so we don't really worry about this. Another type of testing, usually performed by your own team, your development team, is called regression testing. Now, this type of testing is going to be performed just like any other, feature functionality testing that you would normally do, but this is going to happen every time a new feature is implemented or a feature is updated. Well, the problem is that when new features are introduced or old bugs are fixed in your code, well, of course, you're going to be deploying some software patches or updates. Now, the issue here is that any code change might break something that was previously working, like having, unintended side effects, or even it could introduce new vulnerabilities in your code base. So regression testing is going to be a type of testing designed to make sure that any new changes don't introduce security risks in previous code. In other words, well, we have this new feature, it works quite well, we've tested it, but let's just test everything else we've done before it, just to make sure that we haven't broken anything that was already tested. Now, of course, you should do regression testing anyway, not just for security reasons, but just to make sure that a patch that you've deployed doesn't break some fundamental previous feature that was working quite well in your application, like those nasty Windows updates that you happen to read about or even experience them on your own machines, that sometimes when a new update is released, a few users around the world are going to end up not being able to start their computers anymore. That's one example of regression testing gone bad. Or not at all, but we probably don't expect Microsoft to completely ignore regression testing. We just expect them to do it badly, right? And another way to perform software testing is through reverse engineering. Now, this is a very generic term. You've probably heard it more than once before in different contexts. And well, the purpose of reverse engineering is to attempt to deconstruct compiled code into its original source code, or at least to deconstruct it down to a certain state where you're able to figure out what that code is supposed to do, what are all the possible branches, all the possible decisions, or the possible end states in that code. And generally, you use it just to figure out what that code is supposed to do, what it was designed to do. Now, as you can probably guess, reverse engineering is not only useful for software testing or generic software testing, but very useful for analyzing malware, especially those 0 days attacks where you don't know anything about that piece of code. You don't know what it does. How does it interact with your files, with the operating system, with the network connections? But if you're able to drill down into the code of the malware itself, you can see all the potential branches, all the potential outcomes of executing that piece of code, and you can easily then determine if the outcome or any outcome of that piece of code is malicious or not. And as we've said, reverse engineering is actually a very, very generic term, and we actually have about at least 3 levels of code. Now, the first one is called machine code. This is going to be the actual contents of the executable file. That's what you have on your disk when you want to run that application. That's going to be machine code that's taken by the operating system, given to the CPU. That's the compiled program with enough instructions to be executed step by step from the beginning to the end. Not so easy to understand by automated tools, by not to mention human eyes almost at all, but the compiled version of a program is usually the toughest one to deconstruct and analyze. So we also have something in between, which is assembly code. Again, this is going to be native processor instructions, but are going to be presented in a more human readable language. Now, assembly language kind of looks like this. It's definitely not the most user-friendly or programmer-friendly programming language out there, but the main advantage is that you get the chance to program. Now, assembly code kind of looks like this. It's definitely among the least user or programmer-friendly programming languages out there, but it gives you the opportunity to directly program instructions as close to the CPU as possible. So you're basically just telling the CPU what to do. Now, most operations, most instructions in assembly code refer to moving data or performing basic math operations. You know, like push, move, or logical operations like AND, or XOR, NOT, and so on. Now, these instructions use either the CPU registers or the computer's memory. A disassembler is a piece of software that is used to generate assembly code from a compiled program. Again, not so easy to read and understand, specifically since this piece of code right here was written by me around my second year of college, and since I did not add enough comments in this piece of code, I absolutely have no idea what this code does. So don't follow my example, comment your code, please. Finally, we have high-level code, which is mostly going to be written in, programming languages that you've heard about, like C, C++, Java, Python, C#, and so on. Those are considered to be high-level programming languages. A decompiler is the piece of software that is going to try to deconstruct a compiled program into this high-level source code. This is definitely not always possible. And there are specific programming languages out there that are better suited for this type of reverse engineering than others. Now, probably the most popular tool for reverse engineering is the Interactive Disassembler, or IDA, also known as IDA Pro, from Hexrace. Now, what you're seeing here on the screen is the deconstruction of the Notepad executable in Windows 10. And to be more precise, this is actually the replace all functionality, the replace all function. And these are all the possible code branches and all the possible decisions that can be taken by Notepad whenever you are about to replace some text. And if you think that's complicated, have a look at the save file functionality, the simple functionality that basically takes your input and writes it into a text file on the disk. And just have a look at how complex all of this is, which should give you a better picture now of why is it really important to have the proper tools for this type of code analysis or code testing. Now, this is a very simple functionality from Notepad. Imagine what a complex piece of malware can do. Now, one more important idea here is the sandbox, because in cybersecurity, and especially when reverse engineering malware, this is most likely going to happen in an isolated environment, which can be a virtual machine, a container, some isolated environment where you can, and the official term is detonate, the piece of malware, the executable code, and just analyze, see what it does, what kind of network connection it initiates, what kind of files it tries to write on the disk, if it tries to encrypt some files in case it's a cryptolocker, if it creates some auto-run entries, some registry entries, stuff like that. All of this happens in a sandbox because a sandbox is a completely isolated environment. We can let the malware do its thing, whatever it intends to do in there, and then we can easily observe that behavior and understand what that piece of malware actually does. And ideally also how to mitigate it. And another reason why you might want to consider sandboxing, apart from the fact that IDA Pro, for example, is quite difficult to use, in some situations you might encounter some measures in place that can make reverse engineering close to impossible. Two of these situations are code obfuscation, which is a way to make the code extremely difficult to read and to follow. You randomize function names, variables, anything that you can mess up in that code, as long as you keep it functional, so that anybody who manages to get their hands on that code is not going to be able to determine, at least not immediately, what that code does. Second situation is when you encounter code encryption. Now, you can deliver encrypted applications, but if you want to allow your users to use those applications, you also have to deliver the encryption key as well. And even though it kind of sounds okay, like you're delivering something secured, and you're also giving the key to decrypt and use that application. The reality has proven that there is absolutely no situation in real life where you are able to deliver the encrypted code as well as the decryption key, and also to keep that key completely hidden from anybody else who might want to, reverse engineer that process. And this is basically how DRM, digital rights management, is defeated nowadays. Even if you deliver Netflix encrypted content, you do have to provide the key somehow, and you're not going to be able to hide it so well that nobody else is going to find it and actually decrypt that content. And this is why most situations DRM nowadays can be defeated. Now, I promised you we're going to be talking about dynamic analysis, and this is it. Now, dynamic analysis is all about looking at how the application is running. So we're talking about compiled code, functional code. We're looking at the application and at the system as well to see how the application is behaving. Now, one way of doing this, even from the very start, from the development phase, is by using a debugger. Now, the debugger is a program that attaches to your main application and watches or allows you to watch how the execution unfolds. For example, it's going to allow you to step manually or automatically through the program code line by line and see how the application behaves while watching for specific variables or specific function calls, or just checking how the memory is used. Now, another type of testing here is going to be stress testing, or also known as load testing. Now, this is mostly going to be performed pretty close to the end of the software development process, because we need a functional application to be able to stress test it, to be able to throw a bunch of input to that application, and also to make sure that it's not going to crash and it's still going to process it properly. So stress testing works by just throwing some input at that application and see how it behaves. If the performance decreases, when does it decrease? If there's a point when the application actually crashes, or there's a specific point where the application starts to lose functionality, perhaps by not being able to process all that input in a timely manner. Now, this is very relevant not only from a performance perspective, because you're going to have to fill in some data sheets perhaps and tell your customers that these are the minimum or the recommended requirements for your application. This is also something that you get from stress testing or load testing, but also from a security perspective, because in some situations this is the exact same behavior that's going to happen when your application is under a denial of service attack. How is it going to react? Is it going to fail in a safe manner, in a secure manner, or is it just simply going to allow all traffic in case it's some sort of a traffic filtering solution? All of this is very relevant for cybersecurity as well. And nowadays we also have an additional parameter, so to say, that we need to think about. Most of the applications nowadays can or already run in the cloud. Now, clouds are elastic by nature, which means that the moment you need more resources, you can just ask them from the cloud and you will receive them. Now, this might sound nice, but this might also cause you some concern if your application is under an attack or a denial of service attack. You don't want to just scale your application and start paying for a bunch of resources, extra resources, simply because your application is under attack. But stress testing like this performed in a cloud application can also help you determine where exactly does that auto-scaling process kick in. So when can you expect to pay more for the necessary infrastructure that runs your application? Not just in case of an attack, but also in case, you just get a bunch of users, new users one day. And another very interesting software testing methodology is fuzzing, also part of the dynamic analysis. It's just another way to test an application against bugs and vulnerabilities, but this time by throwing various inputs at it. So we're not talking about quantity, but we're talking about diversity, how diverse your input can be. Because this is a great way to properly sanitize inputs that were not specifically designed for your application. A lot of the attacks, a lot of the exploits nowadays happen because the input is not properly sanitized and is most likely obfuscated or masked in some manner that wasn't taken into account when the application was developed. One example here would be a web form that expects me to enter my name. Well, the developer expects me to enter a name of up to a number of characters. What happens if I enter a 1,000,000 character name? What happens if I enter a number? What happens if I enter HTML code or XML code or JavaScript code? What happens if I enter SQL code in there? What happens if I craft a request that instead of the name, I actually embed an entire executable file in there? What happens to the application then? This is where fuzzing helps us a great deal. So as you can see, this type of testing is very useful because it can help us test for very specific corner cases. Also test for unexpected input that can lead to, or at least facilitate, future attacks like code injection, buffer overflows, SQL injection, and so on. And as you can see, we do have a number of fuzzing techniques here that you should know about. First one being application or UI or user interface fuzzing. This is about testing everything that the application interface accepts as an input on any input field, text fields, text boxes, web forms, anything else that can be directly interacted with by the end user. Second one is protocol testing. This is going to be about how does the application behave when the protocol, the communication protocol that the application uses, starts sending abnormal traffic. Think about testing with unexpected values in TCP headers or HTTP headers, unexpected flags that shouldn't be used in specific scenarios, things like that. Again, this is useful because many attacks can be detected at the protocol level. Many IDSs or IPSs are actually looking for protocol anomalies in order to determine known and unknown attack patterns. Even if I see an abnormality in that protocol and I don't know exactly what kind of attack it is, I know that that protocol shouldn't behave like that. It might be someone attempting to exploit a vulnerability, so I'm going to deny that traffic. But first, we have to detect it, and if we don't detect it and if we don't stop it, then we have to make sure that the application still behaves properly in case somebody starts sending some abnormal protocol traffic to our application. And the third one is about files used as input. Many applications allow their users to upload their files, even if it's just a profile picture or a resume or some MP3 file or anything that can be uploaded from the user's hard drive to the application. Now, how does the application behave in case it doesn't receive the expected file format? Or how does the application behave in case it receives an expected file format, but we manage to trick it into believing that we're uploading a JPEG file, when in reality that's going to be an executable file designed to exploit a vulnerability? Or even better, how is an application that is supposed to process your resume online behaves when you upload a document, a Word document with macros in it? Now, of course, to be able to design these types of various inputs and to properly test how the application behaves requires two things. First, a very careful design of your input test cases. Now, you can rely on randomly generated input, but this could, firstly, take a very long time, and secondly, you might not even cover all the cases. A better option would be to carefully craft specific test cases, specific packets or file types, depending on your application, its protocols, and its expected attacks. Secondly, you also need to devise some sort of testing mechanisms that kick in after the fuzzing has completed and try to determine whether the application has properly processed those inputs or has crashed or has reached a completely unsecured state, just to validate if, those test cases were actually successful or not. Now, let me show you just how easy it is to perform fuzzing on your own on a simple web application. Okay, so generally, this is how things look like. Okay, we have our PC here on the left, which is running some sort of web browser, okay, because we're testing a web application. And of course, on the right, we're going to have a website, or the web application that we're supposed to test. Now, of course, your web browser is normally going to send HTTP request packets directly to the web application. And the web application, of course, is going to reply directly to you. Now, for this fuzzing scenario here, we're going to introduce a new component in the middle of this communication here. I'm going to call that a web proxy or an intercept proxy. And the purpose of this web proxy is to act like a man in the middle between your PC and the website. So instead of just sending your HTTP requests directly to the website, you're now sending them to the web proxy. And the web proxy is going to assemble its own requests and is going to send them to the web application on your behalf. And of course, any answers that come back from the web application, well, the app is going to reply to whoever initiated that connection. In this situation, it's still going to be the web proxy. So the proxy is going to see your requests as well as your responses. Now, the advantage of using a web proxy like this is that we can not only intercept that traffic and inspect it, but we can actually work with it. We can change it, we can modify the parameters in your requests, and we can even generate synthetic requests on our own. And in our example here, I'm going to show you in a couple of seconds, we're going to use Burp Suite, which is a very sweet application and a very capable web proxy, interception proxy, and actually has a bunch of features, very fun and interesting features here. I'm going to come back here to Burp Suite later on in a later video, but for now we're just going to use it to intercept our requests and then generate a bunch of requests based on that initial request that we captured, just so we can throw various inputs to our web application and see how it reacts, how it behaves. Now, the app that we're going to be testing is called the Damn Vulnerable Web Application, which is a free to download application that is purposefully vulnerable to a lot of exploits and attacks. And in our situation here, we're going to be jumping over to the cross-site scripting stored method here, because this one is just a simple page that allows us to add a name. So for example, if I add my name in here and say this is an awesome website, right, I can just sign this virtual guestbook and the message is going to be stored in a database and shown back to the user. Now, what we're going to do here is we're going to attempt to fuzz the inputs on this web page and see how the application is going to behave when we send some unexpected inputs to one of these two text fields. Now, if you're curious, you can run this Damn Vulnerable Web Application as a virtual machine, or the recommended way, I would say, simply because it's so much quicker, so much easier, is to run it inside of a Docker container, which is exactly what I did right here. You can see the command to run this as a Docker container. The image is publicly available on Docker Hub, and anything else related to Docker, that's going to be a whole different training. All right, so for now, let's get back to Burp Suite. Now, Burp Suite is available as a free edition as well, called the Community Edition, so you can download it and play with it as much as you want. You can see it does support a bunch of features here at the top row, and right now we're interested in the proxy functionality. Now, the only thing I need to do here in this tab is to set intercept to on, which means that right now if I have a browser that points its proxy settings to Burp Suite is going to be able to intercept all those requests and replies. All right, so let's switch back to our browser and let's add another entry here, shorter one this time. And if I click sign guestbook, now you can see I don't have the feedback right away. Well, that's because Burp Suite intercepted my request, and you can see it right here. That's the entire HTTP header that was sent by me and the payload. This is my name and this is the test text that I've added in my comment. Now, starting from this request, we can use it as a template, and then we can change one or more parameters here that are normally sent to the web page and see how the web application reacts to those changes. So what I can do here now is to right click anywhere on the request and select send to intruder. It's mostly a functionality which is designed for penetration testing. That's why it's called intruder, but it actually also does exactly what we need it to do. You can see the intruder tab now has highlighted here at the top. These here are the settings for the location of the website. And if we jump here to the positions tab, this is where you're going to see all the placeholders that can be fuzzed by this intruder functionality. Right now we don't need all of them, so I'm just going to clear everything in here and just select the username, right? We're going to try to fuzz just the username field, and I'm going to say that I want this username field to be considered as a variable or a placeholder for the fuzzing process. Now we're going to proceed to the Payloads tab, and this is where you actually configure what kind of input you want to send during your fuzzing process. So we're going to generate multiple requests. How are they going to be different from one another? And you have a number of options for this. We can start from just a simple list, like how does this website behave when I put my name in here? How does it behave when I put a number? How does it behave when I put some unprintable characters or some, let's say, HTML or JavaScript code and so on. Now, in this case, we can actually do something a bit more interesting, and let's try using character blocks, because this one here is an interesting functionality and actually allows us to start from a base string and then multiply it as many times as we want, just to see how the application behaves when the input that's coming from the users grows to potentially an unmanageable size. So you can use something like a simple string right here, like ABC, and the let's say we're going to choose a minimum length of 50 and the maximum length of 10,000 characters with a step of 50. So it's basically going to multiply the string right here, 50 characters bigger every single time, and see how the application reacts when the name gets longer and longer. And that's pretty much it. All right, let's click on Start Attack. And here are the requests coming in. Now you can probably see we're up to 600, 700 characters already, and the delay is more and more visible. So the application is struggling to process this input more and more with every request. Now, for now, you can see the status is still 200, which means that the HTTP request is processed, is accepted, but at some point here, if we just let this run for a while, we're probably going to hit a mark where the application is going to start throwing errors. Maybe the database is going to start returning timeouts, and basically that's where we're going to figure out that this is a type of input that our application cannot handle. Now, normally, if you look at the behavior like this, this is something that you shouldn't allow your users to do from the very beginning. So you shouldn't just allow a user to upload a 2,000 character username to your guest book or to your web forum. This is some sort of input validation that you're supposed to do on the server side. Don't let just anybody upload whatever they want into your database. And if you want, you can also have a look at how the actual request is going to look like for each and every attempt right here. All right, let's cancel this one. All right, so we're back here in the fuzzing page for Burp Suite, and we're gonna go and disable the interception. All right, we're gonna set intercept off, and if we go back to our browser, we can see all our inputs here generated by the fuzzer. They ended up in the database, which they shouldn't have if we had some proper input validation, but nevertheless, this is how you can properly fuzz any kind of input, at least to any web application. Right, give it a try. Play with Burp Suite on your own. It's free to install. The damn vulnerable web application is also free to try. Just play with the fuzzing functionality. Now you can probably guess that this fuzzing, as we just described it, it can also be used as a brute force attempt to break into the login page into a web application. Now, don't do this with publicly available websites. Play with your own lab, play with the damn vulnerable web application. Just don't do it in real life, because you're gonna run into some trouble. All right, to wrap things up, when looking for problems and vulnerabilities in your code, you're probably going to be looking for issues in one of the following areas. Starting with authentication, this is most likely going to be the first one to be under attack. Look for specific situations where authentication could be bypassed, or access to specific resources which don't take authentication into account. Also, make sure that the process of validating identities, user identities and user profiles is performed in a secure manner, cannot be overridden, and also that you're not transmitting credentials in clear text. Secondly, injection flaws. This also comes down to what we talked about in the previous episode about input validation. Always sanitize any type of input that you receive from your users, and also always do it on the server side. Don't trust your users and don't trust their clients. Validate that anything that you receive from your users can be safely processed and doesn't contain some hidden executable code. Authorization is about permissions. Make sure you check permissions and make sure you check that every privileged operation is validated before it is allowed and executed. Also, make sure that you're not allowing your users to impersonate one another and to temporarily borrow the permissions from a more privileged user. Now, when talking about privilege escalation, this is exactly where you're supposed to focus your efforts. Error handling, again, it's about providing just enough information to your users, to your legitimate users, to understand what went wrong, but not enough information for a potential attacker to understand how your internal security processes work. For example, never tell a user if just their username or just their password is wrong. If an input received from one of your users doesn't comply with your requirements, don't give that user the entire SQL statement that failed or the entire log entry that shows what kind of processes are running in the backend and where the application issue actually happened. Normal users don't need to see this. Normal users don't need to see what's behind the curtain. Don't forget about encryption. At rest. So when you store data for long term, for short term, even when you store data on the user's devices as a cache, a temporary cache, for example. And also don't forget about encryption in transit. Whenever you're communicating data, when you're transferring from your users to your users or to any other third party, I don't know, maybe cloud services or other companies that you might integrate with, other products, always communicate securely. Use encryption and use strong encryption. Logging and auditing, don't forget about this either, because this is what helps you pinpoint problems in your software and also helps you determine if you have any performance problems, if you have been breached, if some users are experiencing problems even before they start complaining. Always have proper logging and auditing in your applications, but make sure it's performed in a secure manner. Don't allow just anybody to view those logs, to access them, or not to mention this dreadful scenario when a user can actually delete those logs as well. Don't allow users to delete their traces. Log everything, trust no one. Session flaws, we're going to talk more about this. We're going to talk about session hijacking, but mostly this is going to be about protecting the actual identity of a user while they are interacting with your application. Make sure that another user, make sure that an attacker is not able to impersonate a legitimate user, is not able to guess their session identifiers, is not going to be able to take over their session and compromise their accounts. And finally, the last one, but by no means the final topic here, but we've reached the end of the slide, is insecure configurations. Now, insecure configurations can mean any number of things. Now, insecure configurations can address defaults that come pre-configured from the software vendor, test accounts, test data, or simply having specific security functionality implemented in your application but not enabled by default. Don't trust your users to be so security savvy and so, let's say, security oriented. Make sure that by default, you're providing them with a secure application, a secure environment. It doesn't help anyone if you do have that functionality in there, but nobody is using it. All right, that's it. Make sure you understand and that you're able to explain to yourself, at least, all these different testing methodologies that we've covered today. Thank you so much for watching, and I would gladly see you next time when we're going to talk about mitigating specific attack types in networks, in applications, and even more. Thanks for watching. Like and subscribe if you found this useful, and see you next time.